and this will be our first slide when we get going on the recording. Not there yet. Okay. It's been a whirlwind since we met last. I mean, I had all sorts of things to do to get ready for the meeting and had to get it done by the end of business on Thursday, so it was pretty miserable. So sorry we missed class. I don't know if you want to try to make it up or just go with the flow. Somehow, I'm so surprised y'all said that. Okay, we'll live with that. Well, if there's any way we can, we'll try to. So let's recap where we are, where we're heading. Okay, we finished chapter 15. I think all 4 of you have turned in the labs from that and done quite well. And we did the test on that. Chapter 14, okay? And chapter 15, we were working on the lab for that. We didn't quite get it finished, so we're going to finish that right now. Then we'll start in 16, and then no later than 3 o'clock, though, we'll stop 16, and I'll give you the test on 15, okay? And y'all know you can have formula and equation sheets, so hopefully you have those already. If not, you have some time between now and then.
I don't really understand what you're talking about.
You can write anything on a piece of paper you want to have in front of you during the test. Yeah. I mean, words, definitions, relation, I don't care. Whatever you want to write on a piece of paper, you can have with you. In the old days, they called it a cheat sheet. Okay, I don't know what you want to call it. I don't like calling it that. It's just, here's my theory.
It's a reminder.
Yeah, here's my theory on learning. I'm not a big believer in memorization. I mean, I need to know my phone number, my house number, and a few things like that. But the rest of it, I want to look it up. I don't want to try to memorize anything. Number one, the old gray cells ain't what they used to be. I can't count on them. So, and if you were working for me, I said, hey, we've got this problem here. Fix it. So, I think I remember the formula for this. No, I want you to look up and make sure you got the right formula for that. So that's why I don't mind you doing a formula and equation sheet, because frankly, that's the best way to study that I've found so far, is because very rarely, but when I was an undergraduate, occasionally I had a professor who allowed us to have a formula and equation sheet. So man, that night before that test, before I was doing homework and stuff like this, but that night before the test, I was trying to put it all together, get down the most important things, put them in an orderly manner so I could find it easily, writing as small as I could. I'm a really sloppy writer, so I had to get it down as neatly as I could, but as carefully as I could, as small as I could. And by the time I did all that, when I went into the test the next day, sometimes I'd forget to look at it, because that was the best review I could have possibly had. So I highly recommend for every test you ever take, do a formula and equation sheet, or whatever you want to call it. Because whether you can use it or not, you may not be able to use it, but by doing one the night before, you tie it to the other synapses, and you'll know the material better than if you just read it. Because reading it is passive, writing it down is active. So I figure I want to encourage you to do that. So that's what I mean by that, okay? And you can use it in this course, okay? Other courses you may not, but still not a bad idea to do. Okay, so everything copacetic for today so far. And I can't wait till I check on my attendance to see if they've finally taken out the other people, because they sure should have. Let me get some of this stuff in the right order. All right, sorry. I should have had this done this way before. Things have just gotten piled on my desk. Almost there. Just did not want to get things out of anywhere where I might lose them. I wanted them where I needed them. Okay. Well, the whole reason I did that was to get to today's lab. Now I got right up to it and put it aside. All right, motions of the sun. All right. Now I've dropped these on the floor. Finally, things are where they need to be. All right. Help me with my memory, because it ain't good. I think we had finished table 48.1 at the bottom of page 376, had we not? We were working on it? Oh, okay. What's that? Okay. Have we done, okay, we had done declination of the sun on February the 15th and June 21st, but we hadn't done it for October 15th. Is that right?
Right.
Had we done noon altitude of the sun at your location, February 14th, 15th, and June 21st?
Yes.
But we hadn't done October 16th, 15th. And we hadn't done anything at Alta Guard, Norway. Okay, got it. All right. Okay. Then, look. Okay. I think what I was using was this. I should have left it open from this morning, but I didn't. But it came right up. That's good. So let's do the slideshow from here. Okay. So page 376, table 48.1. We've done February 15th, first two columns, June 21st, first two columns. All right. Okay. Yeah, we will need this. So, whoops. Okay. That's a pretty lousy globe. That's a little bit better, but not much. That's a reasonable horizon. That's a somewhat of a meridian. We're standing right here in Bessemer, Alabama at, anyone remember? Excellent. 33 degrees, 23 minutes, 45 seconds. Excellent. Okay. Here is our zenith, and that much below our zenith, 33 degrees, 23 minutes, 45 seconds, is what? Celestial equator. Because here's the equator on the globe, and we're 33 degrees, blah, 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 north of it. So the celestial equator is 33, 23 south of our zenith. Good deal. All right. How do we get declination of the sun on October 15th? How do we get that? Declination of the sun on October 15th. Yeah, flick back one page. What's that figure 8 called? If you're on 374, it's in the first line of its caption. Analemma. That's the good old analemma. So turn to the analemma and find, what did they say, October 15th? Find that. Anyone located it? 8 degrees south. That looks pretty reasonable to me. So you fill that in on the table. You can say 8 degrees south, or you can say minus 8 degrees, whatever you want to call that. What do we do on our ugly little drawing here? And by the way, there is one other piece of information we need, because the question is the noon altitude of the sun at your location. Altitude would be how far above the southern horizon it is. There's the southern horizon. Here's the northern horizon. Okay? So we also need to know something about that other angle there. How do we get that? Okay? This angle here. Subtract this one from 90. Very good. Except, do we really do 90? No, I do. 89 degrees, 59 minutes, and 60 seconds. And that is 90 degrees, because 60 seconds is a minute. That would make 60 minutes. 60 minutes is a degree, so that would make 90. All right, and we subtract from this our 33 degrees, 23 minutes, 45 seconds. It also makes the subtraction so easy. What does that give us? What's that subtraction? Oh, come on. You don't need a little black box. What is it? 56 degrees. 36 minutes, 15 seconds. Okay, so this angle right here is our 56 degrees, 36 minutes, and 15 seconds. All right, let's go back. Okay, we said it's 8 degrees south. South of what? Of the celestial equator. So where would it go on here? Just below it. 8 degrees is pretty small, so I'm just going to draw it in about like that. There is the sun on, is it 15 October? Yeah, 15 October at noon, or anytime. It's 8 degrees below the celestial equator. That's why it's a minus 8. Okay? So therefore, what's the altitude of the sun above our southern horizon at noon on that day? Minus 8. You got it. That's why I wanted that in there, so it'd be easy to do. Subtract the 8 degrees from that. Okay, and what would that give you? 48 degrees, 36 minutes, 15 seconds. There you have it. All right. That's the noon altitude of the sun at our location. Okay, that was in the fall. Let's move to the winter. And we're going to December 22nd. The first thing it asks for then is declination of the sun on December 22nd. How do we get that? Second? Yes, you don't even have to look, do you? That's right at winter solstice. So that is minus 23.5 degrees, or minus 23:30, or 23:30 south, or however you want to say it. That's the declination of the sun on December 22nd. Okay, so that's something about like this: 23 degrees 30 minutes south of the celestial equator. So, what's the noon altitude of the sun at our location here where we live? Again, we're going to need to use 5636, right? But this time we're going to do what? Second? A little louder. Yes, we're going to subtract the 23 degrees 30 minutes from that. Second? From 90 degrees? Well, if you subtract this from 90 degrees, the declination of the sun isn't from the zenith, it's from the celestial equator. So you go where the celestial equator is and subtract that from that. Okay. And that was at 56, 36, 15. Subtract 23, 30 from it, and what do we get? Second? 33 degrees. 6 minutes, 15 seconds. That's where the sun is on December the 22nd, where we live. That's not very high, okay? If we're standing here, look, there's a zenith directly overhead. 33 degrees is barely a third of that, just a little over a third of that. So it's not very high on December. And that's at noon on December the 22nd. Okay? All right. Now put on your heavy clothes because we're going to Altegard, Norway. Why would you want to do this thing like that? Okay? What do they tell us about Altegard, Norway? Say that again. All right, latitude 70 degrees north. That's good to know. All right, I'm going to get rid of all this stuff that pertained only to us. Now we will need use some of the information we gathered earlier, but you got it written down. I'm sure of it. So I'm going to clean up as much of this. Ooh, I probably didn't do that, but it's okay. It's all redoable. All right, I think I pretty much cleaned it up. Oh, I cleaned up the wrong thing. Okay. You know what? Before I do anything else, I'm going to make a better globe down there. I'm going to try to anyway. No guarantees. That's a little bit better, not much. Okay, I'm going to put on some real heavy clothes. Okay, all right, because it's cold up there. Okay, all right. Huh? Oh yeah, hat. Okay, okay, got a hat on too. Okay. Now, when they told us it's at 70 degrees north, that means north of what? Our equator. Okay, so on the globe here, this is something like that. This is the equator, and this would be 70 degrees north of the equator, which means on our little drawing here, celestial sphere, what do we put where? Okay. How does this relate to something that we need to draw up here? 70 degrees from that is going to be
30 degrees off the horizon.
what? Yeah. Well, what is that? That's 70 degrees off of that. Celestial equator. I'm sorry, I don't hear well. Okay, so I think this is about right. Does that look about right to you? I don't know. Let's just call that 70 degrees. There's the celestial equator. When you're at Altegard, Norway, celestial equator is always there. That means this is at, subtract from 90, 70 from 90 is 20. 70 from 100 is 30. You're doing your grades, right? No, okay, all right. So that'd be 20 degrees there. All right, let's go back to February the 18th. You have already written in what the declination of the sun is on that day, and what did you have written down for that day? Second? 13 degrees south. So 13 degrees south of the celestial equator would put you right about there. Here is the sun at noon on, what was it, 15th? Yeah, 15th of February. Altegard, Norway. Okay. How high is that above the horizon? Oh, I didn't label it. What did you say it was again? 13 degrees. Okay, so how high it is above the southern horizon? Mine's not to scale. This is 27 degrees. 7. February the 15th, you are 7 degrees. The sun at noon is 7 degrees above the horizon. Right about there. I mean, this is high as it gets. It comes up probably about 10:30, 11. At noon it's there and sets just a very short. That's all you get, folks, on February the 15th. Okay? On June 21st, what did you have the declination of the sun be?
3.5.
North of the celestial equator. So the celestial equator is there at 20, so we go another 23 and a half north of there. Okay, so that's the sun on 21 June. Okay, when you're in Altegard, Norway. Okay, so what would that be above the horizon?
Plus 23.5,
43 and a half. 20 plus 23. 20 degrees, the celestial equator is above the horizon. Another 23 and a half. The sun is above the celestial equator. So that gives you a total of here of 43 degrees, 30 minutes above the southern horizon. Now, glance back at the noon altitude of the sun at our location. On December 22nd, we were just barely below that, okay? On February the 15th, we were above that, weren't we? I don't have it written down. And October 15th, were we above it then? So at their highest point of the year, they're just barely above we are, where the sun is for us, at the lowest point of the year. Okay, a little bit above, but not much. Okay? How about the next one, October 15th? Where's the sun then? 8 degrees south of the celestial equator, so that would be something about here. So here's the sun on, what was that date? 15th October? Okay, and that was, too many lines here. This is 8 degrees south of the celestial equator. So what would that put the altitude of the sun on that day? I know there's a lot of numbers there. This is 20 degrees north. You go 8 degrees south of that. That leaves you more like 12. Okay, 12 degrees. Okay, so that would leave you at 12 degrees north of the horizon on the 15th of October. Not very much. A little bit higher than it was on February 15th, but not a lot. Then the sun would probably come up about 9:30 in the morning instead of about 2:30 in the afternoon or something like that. Okay? I'm guessing on those. I don't know those for sure. Okay? Questions? I'll be glad to go over anything because I know I'm getting sloppy up there. I could erase them so you can see them easier. Would you like me to do that? Okay.
On the first,
On what?
just on our location, we did degrees above the celestial equator and below the celestial equator. With the answers for this one, we put above the horizon.
Okay, wait, okay. Altitude of the sun is always above the horizon. Okay. Declination of the sun is below the above or below the celestial equator.
Are we doing the declination or are we doing the...
Okay, we already did the declinations. We did the first two last Thursday, and we did the last two this Thursday, today, right? But you already filled in declination of the sun for all 4 days, right?
Okay.
That's that first column right after the dates, declination of sun. That is above or below the celestial equator. Plus is above, minus is below. Okay. Now, altitude of the sun, either at our location or at Norway, would be above the southern horizon. So that's where you flip over from the other thing. So altitude is always above the horizon. Declination is above or below celestial equator. Okay. Got it? Now the question. What is declination of the sun on December the 22nd? South of the celestial equator. Here's the celestial equator. When you go 23.5 degrees south of that, where are you? Below the horizon. That's at noon. The sun is somewhere below the horizon. It never comes up in Altuar, Norway on December 22nd. Ever. So you can put, if you want to, minus 3.5 degrees below the horizon. That doesn't really make sense. You can just, okay, no, it's 23.5 degrees below the celestial equator. Celestial equator is 23 degrees, so that would make it 3.5 degrees below the horizon. But you don't have to put that. You can say never rises. Never rises. Don't see it. 24 hours of darkness that day. Okay. Right around noon, you might get a little bit of lightning like you do at 4 o'clock in the morning or 5 o'clock in the morning here, but just before the sun comes up. But it never comes up, okay? Unless at noon, you get that little bit. The rest of the time, pitch, black, dark, whatever the moon and the stars are showing. And that's all, folks.
I love watching PBS.
Uh-huh.
There's some little town that's behind like a mountain.
Right.
And it only gets like 2 days of sun a year or something like that. Because the mountain is so many.
Oh, I see.
So when the sun reaches that peak,
Yeah.
they get just a little glimpse of sun then.
Oh, my goodness. That must be miserable. And people live there. Oh, wow. It's amazing. Okay. All righty. Everybody got what they need? Table 48-1. Okay, turn to page 377. And I'm going to, again, do a bunch of erasing here, but try to keep as much as I can of what we need. Okay? Because I know what's coming up. Okay? I don't think I'll need any of this. I will need my celestial sphere and that kind of stuff, but I won't need these things. Okay. Let's go into lore, okay? Rip Van Winkle, I don't think he ever really lived or he existed, but it's a tale, awakens from his extended slumber. Y'all know who Rip Van Winkle supposedly was, right? The guy who slept, what was it, 70 years or something like that? I mean, it's ridiculous. but he awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. Okay? The passerby, notice, quickly responds and rapidly moves away. If I'd been sleeping that long, I don't think I would have smelled too good either, or looked too good. Okay. Realizing, no, it's not 70, 20 years. Realizing a 20-year snooze might be a world's record, he thinks he should pin down the date, because just that number of years, someone else may have come pretty close to that. I doubt it. But he wanted to pin down the date as well as the year. All the other guys said was a year, and then he moved on really fast. He moves out from under the tree where he slept, and good old Rip happens to have a sextant with him and measures the altitude of the sun when it crossed his meridian. In other words, when it reached the highest peak in the sky, that's when it crossed the meridian. And he found that was 44 degrees over the southern horizon. All right, so he knows this. I'm just guessing at it. This is the sun at noon. He doesn't know what day it is, though. And this is 44 degrees above the southern horizon. Have we drawn it right? I'm not asking for accuracy, but just you got what it's talking about. He knows that the latitude of his chosen spot on the Hudson River in New York was 42 degrees north. So that's why I needed this little thing down here. This is the equator here, and he is 42 degrees north of the equator. What would that correspond to here? No, not yet. We're not there for date yet. But what can I draw here that corresponds to this down here?
Subtract 2 degrees, and that would be the celestial equator.
Okay. From where?
From the noon.
From the zenith? Is that what you said?
From the,
yeah.
Right across the meridian.
Okay. Yeah. Okay. See, he's standing here. His zenith is right up there. He's at 42 degrees north of the equator. That's the equator here. So you want to do 42 degrees that way will be the what? Celestial equator, exactly. I'm hard of hearing, so I can't hear for sure what you're saying. So that's going to be something like this. Okay? He is 42 degrees north of the true equator. So on the celestial sphere, he needs to be, the zenith is directly over him, that needs to be 42 degrees above the celestial equator. This corresponds to the latitude down here. Then you subtract to get how far it is above the horizon. Okay? So this is our 42 degrees. And what did you say this was? Celestial equator. Right? All right. Now, do you need to learn this angle here? It might be helpful, right? So what would this angle be? .48, exactly. So this would be 48 degrees. So celestial equator is 48 degrees north of your southern horizon on that day. Okay? He got that by knowing his latitude. Okay? What does that make the relationship between celestial equator and the sun at noon on that day? 4 degrees, exactly. 4 degrees is this. Now, obviously, mine's not to scale. That's 40 degrees. The sun is 40 degrees. Which direction?
4 degrees south.
South of the celestial equator. Okay. Does that help us in any way? Go back to your table, to your, what's that called again? Analemma. Go back to the analemma and find out, what's that? Okay, but you see there's 4 degrees south of the celestial equator. You see that? Okay, so you can go across here and you run into a date that looks like about October the 4th, but if you continue on across there, you are around second? I don't think it's February. March. Yeah, it looks like a little above the 10th. I would say the 11th, but I don't know. Somewhere in there. Okay? Guess what you've just done? It says, on what 2 possible dates could Rip Van Winkle have awakened? What do you say they were? October the 4th, I thought you said. And March the 10th or 11th, right? Okay, so be sure you put both of those down. That's the first and only question we've run into so far. On what 2 possible dates could he have awakened?
It says that there were.
That's what I thought you said, October 4th. You see it on the analemma? 4 degrees south of the celestial equator. Go across there, and sure enough, it looks like October the 4th. And then they go across to the other side, and that looks like about the 11th to me of March. Okay?
It
Then,
says that the tree that he slept under had buds. So
so that's probably spring. So what is the date of his awakening?
I'll say March 10th.
March 10th, 11th, whatever that is. But be sure you answer all the questions there. So you had 2 and you chose 1. Okay, good. All right. That's enough for that. Okay. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma in figure, here they just messed it up completely, figure 48.4. They have 4.5. I don't know where they got that. 48.4, okay? To see that on October 15th, they just picked that date again, they used it earlier. What is our time? You go this to the top of the chart, from October 15th, follow that line all the way to the top, and what do you find? October 15th, follow that vertical line all the way up, and what do you find? What do you see at the top of the chart? A Taylor Swift song. No, that's a different chart. Okay. 14 minutes. Okay, what does that 14 minutes mean? The sun will cross the meridian 14 minutes before. It's on the left of it, before clock noon. Okay? That's the time in minutes before clock noon. So actually the sun crosses the meridian that day, not at 12 noon, but at 11:46. Okay? That's when it would cross the your local meridian that day. See how that works? All right. For the dates given in the table below, use the analemma in figure 48.3. That time they got it. No, it should be 48.4. Sorry. 48.4. To determine whether the actual sun will cross the meridian, that's as opposed to the virtual sun. Okay, never mind. Before or after clock noon, and then by how many minutes. So first, the middle column here, you write one of 2 words. Well, you might write one of it. It's either before or after. It's conceivable you could be right on, okay? But it's usually either before or after. And then the last column, how long before or after, Okay? So what you write in the middle column is one of two words, before or after, unless it's right on the at noon, and then the other would be the time before or after clock noon. So let's first do January the 10th. Where do you find January 10th? Way down there, okay? Go all the way up that vertical line, and I can't stay on the... Yeah, that's what I was seeing. Yeah, it looks like about 7... Oh, wait. The first question is asking what?
Before or after?
Before or after, and what do you put?
How would you figure before or after?
Okay. I look at the example they gave me before that. They said on October 15th, you were before clock noon. October 15th, yeah, you're on this side before. On January 10th, you're on that side, so it's after, right? Okay. Okay. Notice the example they give right above that. On October 15th.
As you pointed.
Okay. This example here, October 15th. Go to the NLM. There's October 15th. Okay? Go straight up here in your 14 minutes, and they tell you here that's before clock noon. So that means anything on this side of the table is before that side of the table. Okay? So in that first column by January 10th, what word do you write? After. And then in the second column after that, what do you write?
7 minutes.
7 minutes. Very good. Okay? Y'all want to try the rest of them on your own? You can work as a group. 1s, 2s, 3s, or 4s. Okay. I think it's even less than one. A few seconds maybe. And that would be after. But yeah, it may be close enough to 1. 1 minute will do, yeah. Something pretty small and after. Just barely after. Okay. Okay. Sounds about right. What's that? Before? Okay. There's September 5th. I can't tell which way. I think it's on the uphill side of the little black thing. Then the 4th, 3rd, 2nd, 1st. I think it's just across on the looks like to me it's just over on the after side, but I don't know. It's so close, I'll give you credit either way, okay? Just don't have it 45 minutes in there or anything like that.
What if it was 0? 0 minutes.
Okay, then you say it's right on clock noon. Yeah. And we'll run into one of those, I think, in the next set. They get really picky. And look, if they did October 30th, okay, that's a little bit later. Okay, it looks like it's before, I agree. Way before. 16 minutes, sounds good to me. All right, that wasn't too bad, was it? Everybody concur on that? Flip over to the one we've been dreading, the last one, okay? Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian on the dates in the table below. So we got to go back to our situation, which means erase a lot of this. Okay. I'm going to leave the cold weather clothes on even though we don't need it. It's way too hot now, but just because I don't want to take them off. Yeah, that's what it's asking for, so we got to do our drawings again, right? Where do we begin? At our location. Where's that? All right. There's the equator, and it's 33 degrees, 23 minutes, 45 seconds. North of the equator. So what do we draw on our celestial sphere here? Not really a sphere, but the picture. Where's that measured from? The zenith, because that's where we're standing. So we do, I don't know if that's right or not, but let's just say it is, 33 degrees, 23 minutes, 45 seconds. I said seconds and wrote the symbol for degrees. Where did that come from? Okay. That would be the angle there, reflecting the angle. And that would make this right here what? What does that indicate? Celestial equator. Very good. All right. Now, sun altitude. May 15th. There's no table that gives us that directly. What are we going to have to do? On May 15th, determine what? Determine the, needs to be something to do with the sun. Okay, the altitude we need from something else. What was the date give us? Guess where we're going to go?
Declination.
Huh?
The declination.
The declination of the sun. And what is declination of the sun on May the 15th? About 19 degrees, yeah, north of the celestial equator. So if that's 33, 23, 45, 19 degrees north of that is going to be a little more than halfway, isn't it? Not sure I got mine drawn well. but that was what we say 19 degrees north of the celestial equator. That's the sun on, was it 15th of May? The what? May 15th? Yeah, 15th of May. Okay, where we live. All right, that comes close to giving our altitude of the sun above our southern horizon, but not quite. What do we need? Oh, yeah, we need to know that big old fat angle there. We did it earlier. Does anyone remember? Or do we need to subtract again? 56 degrees. 36 minutes, 15 seconds. Okay, and then what do we do with that? Add 19 to it. And what will that give us? $75 degrees, 36 minutes, 15 seconds. What did you say? I couldn't hear. I thought you said something. Oh. Okay, that would be the number of degrees above the horizon of the sun on noon on the 15th of May, where we live. Altitude of the sun. What time does it cross our meridian at that day? Which would be 11:56. Very good. 11:56 a.m. Excellent. How about June 15th? What would be the altitude of the sun? What would we look up first? Say again? 23 degrees is our, it's not quite a half. June 15th, we're not quite at the half. I would say let's round it just to 23. Because you see, on the 21st, it gets up another half. So let's just call it 23 degrees what? Of what? Celestial equator, exactly. Okay, so these are pretty close to each other. That would be somewhere about there. So this would be 23 degrees north of celestial equator. That's the sun on June the 15th. Okay, and what would that make it above the altitude of the sun? Okay. Yeah. Oops. Add 23. And the Earth, sure enough, that's 79 degrees. 36 minutes and 15 seconds. Not that that matters much. 79. Almost 80 degrees. Not quite overhead, but pretty close. Okay? How about the time when it crosses our meridian? On June 15th? At noon. I mean, that's smack on, okay? As close as I can see, it's right on the money. Okay? How about November 4th?
South.
15 degrees south, I'll buy that. 15 degrees south of the celestial equator, be something about like that. 15 degrees south, there's the sun on, what was this, November 15th? November 4th. Okay.
Last one we just did was today.
What's that?
June 15th.
What about it?
It's today.
Oh, you're right. I had thought of that. Yeah, so that's right. Yeah. Yeah, so it crossed our meridian at noon today, okay? Well, I didn't. Way to go. flew right on over. Okay? So how do we get the altitude of the sun on November 4th? Say again? Yeah, you subtract it from 56 degrees. Okay? So subtract, what do we say, 15 degrees? And sure enough, that's 41 degrees, 36 minutes, 15 seconds. Okay? So it's not quite halfway up there on November 4th. Jingle bell, jingle bell. How about December the 25th? What's that? Oh, yeah, we didn't do that. Yeah, you're right. What is the time the sun crosses our meridian on November the 4th? It's what? 15 minutes, and which way did you say? Before noon. Okay, which would be? 11:45. Very good. Okay? Now let's go to Christmas. December 25th. What's the altitude of our sun on that day?
23.
Yeah. It's awful close to 23 and a half, isn't it? Because remember, that's a flat-bottomed 8. There are several days in there. It's real close to the very bottom. So you can either say minus 23 or minus 23 and a half. That would be down here somewhere. I don't know if you want to put 30 or not. That's up to you. Okay. Subtract that down here. Okay, and again, I don't know if you want to use the 30 or not. It's up to you. You can either ignore it or not. Okay. Oh! That would be what? $33.06 maybe, or 36, it doesn't matter. Something around there, just over 33 degrees. That would be how far it would be on December. Okay. Now, my drawing's not to scale, but you get the general idea. And what time?
Before.
14 what?
14 minutes before 12.
On December 25th?
Less than
I'm sorry. Mid-noon.
Right at noon, yeah. It might be a few seconds before noon, but that's close enough. Noon is close enough.
Put less than a minute before.
Yeah, you could do that. Yeah. Between 11:50, 9:30 or something like that. I mean, you could do whatever you want to. Good deal. Does that make sense? Reasonable lab? For what? And which answer? The altitude or the time?
Now it's 41.
Find the declination of the sun. You see it's a negative below the south of it, so subtract that from your 56, whatever that came out to be. I think it was 41 or something like that. All right. Good deal. Any other questions? Need to take it home and work on it a little. I can't imagine why, but if you do want to do that, you certainly can. It's due a week from today, but you can turn it in anytime you want to. I'll take it now if you've got it. That's up to you. Any more questions about it? How we got anything? Okay, if not, I'm going to throw away this PowerPoint. Okay? You can see it later on YouTube. What's that? Okay. All right. Chapter 16. Any questions on 15 before we move on? Remember, starting around 3-ish, I will give you your test on chapter 15. Say that again? Stop me at 3, yeah. Okay. Now, y'all need a little break now before we get started? You do? Okay. So I'm going to pause this. All right, we are now recording. Don't quite have the picture up yet, but it's coming. Any questions while we're waiting? All right. We're starting now chapter 16, which, just for a little bit of context, the class is sort of split up. Astronomy, 3 chapters. We've done 2. This is our last chapter in astronomy. Then we'll have, I think, 4 chapters on geology, basically, or earth science. And then we have 1 chapter on weather and climate, and 1 on oceanography, or Earth's waters. Okay? So we're nearing the end of the first segment. Now, when we finish this chapter, typically then, I try to schedule the visit to Samford. Do y'all want to go? Planetarium there, huh? Okay, all right. Well then, if y'all didn't care to, we could have maybe used that day to make up the day we missed. But if you want to go, it's worth it. But if y'all didn't want to go, I don't want to force you to. And we only got 4 people, so it's not going to be a big outing. But that also allows me the flexibility of saying, if you want to bring someone, you certainly could do that too. So if you got a kid and brother, sister, friend that would be interested in it, I'm pretty sure he would enjoy having a bigger crowd. But it's not necessary. Okay. All right. So chapter 16 is the Earth in space. Now, when I reference this chapter, I like to call it the Earth-Moon system, because we're going to talk almost as much about the moon as we do about Earth, because we're a system here in their atmosphere. Okay, the core concept here, in the new edition, at least it's easier to read than it used to be, the way the Earth moves in space is used to define time. Hey, we've been talking about this for 2 chapters now. And describe location of the sun on the surface. Yeah, we've been talking about that too. And it causes other recurrent phenomena, such as the seasons. We've talked about that. So some of this is going to be a review. Some of it may be a little more intensive than what we had before. Okay? And here's a nice little picture here. Again, it's an artist's rendition. But you better believe that's not how they ever really look, okay? The sun, if that was really the size of the sun, it would be so big it would take up the whole space, you'd hardly be able to see anything, okay? Now, I think what they're suggesting here, and I can't tell for sure, but I would think this is Mercury, though it should be closer to the sun, it seems like to me. That would be Venus. It looks smaller just because it's further off. This is Earth. So we must be on the moon looking back at the Earth. Well, the moon actually looks bigger than the Earth. Of course, it would if you were on it, or you're maybe just on the other side of the moon. But the other part of me would say that's Mars, because it's a red planet. It's just way over there somewhere, okay, outside our orbit. Nowhere is Jupiter that close to us, ever, okay. It's big, but it's never that close. Saturn, obviously, with the rings. Uranus and Neptune probably out there. They are so far out there, it's certainly not to scale. But it's a little bit better than having them all lined up in one fat line, okay? Not that that matters any. So let's start with the shape and the size of the Earth. This is 16.1. Every globe you ever see makes the Earth look like it's a perfect sphere. It's not. It's called an oblate spheroid. Almost a sphere, a lot like a sphere, but what are the deviations? It's slightly pear-shaped, a little bit thinner at the top and thicker at the bottom. Just a little bit. Okay? I'll get to the dimensions later. Now this is one I do not understand. It says there's a lump in the Pacific. Okay? The Pacific is all water. When's the last time you saw a lump of water? I can't figure it, okay? But maybe they know what they're talking about. I don't know. It seems like if it was a lump, it would flow back down and go in. It wouldn't be a lump anymore. But then it says there's a depression in the Indian Ocean. It's the same deal. If it's in the Indian Ocean, if there's a depression, why is the water running into it, you know? I don't know exactly what they mean by that, okay? The elevations and depressions they're talking about are less than 85, and depressions are of deviations less than 85 meters. What's 85 meters? About not even a full football field length. You know, that would be all. So it's not much. Not much at all. Here is there's a picture of the Earth. Now, this makes it look like it's really not a spherish at all. But that's because part of this is in the shadow. So this isn't a particularly good figure to have here. But when I look at this, and I hope you can sort of see this, I'm pretty sure that's fairly close to the North Pole. It may not be exactly. It's just a cloud system up there. But this, I'm pretty sure, is Baja Peninsula in Mexico. With this being Mexico, this is California here. I don't know what the deep red is there, but it looks like to be about Arizona or maybe New Mexico, somewhere in there. So I don't know, but that looks like you're just looking at here. So that, to me, would have put the North Pole somewhere more here. So I think that's just a weather system up there. This is mostly Pacific Ocean here. Probably Alaska is sticking out somewhere there. I can't tell for sure. Okay, I think this is a little bit of South America there at the peninsula of the isthmus, you might say, between Central America there. Panama maybe here, and Nicaragua, Costa Rica, Nicaragua, Belize, those countries. So that's my perception of this. That may even be Florida right there. It's so hard to tell. But here's what they talk about. Now, they've exaggerated this like crazy. Okay? If this is a perfect sphere here, the dotted line, then the oblate spheroid means we're a little thick in the middle. I'm used to that, okay? And it's not that funny. Okay. All right.
I'm dealing with the same thing.
You just finished it too, didn't you? Okay. Okay. They've exaggerated this big time, but they show that the difference here, and this is in kilometers, not meters. They were talking about meters there. This difference looks like to be about 42 meters, a kilometer difference in, not quite as long at the poles, a little bit wider at the equator. Okay? Okay, in miles, about 26 miles. So it's not quite a perfect sphere. It's an oblate, meaning sort of flattened slightly, ever so slightly. I mean, when you're talking 26 miles out of 8,000 miles, that's not much, okay? Not much at all. Okay. Now, before we get to the motions of the Earth, the old edition didn't quite have this picture, and I don't know really what to think about this one either. But if you got your new edition there at the top of page 409, that shows the 4 terrestrial planets. What are they? Mars. Excellent, excellent. There, with Mercury being the first one, okay? Though Mars is bigger than Mercury, so I'm not sure I agree with the scaling here. Venus actually looks a little bigger than Earth. It's not. It's just a little smaller than Earth and then Mars, okay? And then relative size, I bet you they got Jupiter about right, okay? It takes up most of the picture, and you don't see but little bits of it. But you do see, lower right corner, the great red spot, okay? So that's what told me that was Jupiter. And then, of course, the next one, Saturn. The rings give that away. Even though Jupiter, Uranus, and Neptune all have rings, they're very tiny compared to Saturn's and not noticeable. And then there would be Uranus and Neptune, who look almost the same, okay? They made them different colors, but they are very, very similar. Now, the perspective is off some, but Uranus and Neptune are still many times larger than the Earth. So they don't look that many times in this picture, but they're getting further away. And of course, they're way too close together, but at least they got the relative sizes probably pretty close to true. Okay. Now, remember the ecliptic of the sun? That's the path that it follows. Because all the planets are in that same disk pretty much, they're usually on the ecliptic. And most of the time you will see, on nights that you can see it, Venus. And the trouble is, they don't show Venus on this one. The brightest object in the sky after the sun and the moon, and they don't show it. Mercury is always right near her horizon, either morning or evening. If you ever could see it, it would be right there, right before or after the sun rose or set. So, but it's on the ecliptic. Jupiter, quite often you'll see Jupiter in the evenings or mornings, and it's usually right on the ecliptic. Mars, right on the ecliptic. I seldom can see Mars until it's Mars. Saturn, nah, it's too far away. But they do show a couple of other pretty major stars there. Regulus, I've often heard of, and Antares, definitely, very bright star. And then there's Spica, which seems to be fairly bright, but I've never heard much of Spica. So anyway, that's just, if you can find those objects, you know you're close to the ecliptic, because there's no dotted line up there that says, I'm the ecliptic. Okay, let's look at now at the motions of the Earth. This is 16.2 on page 410 of the new edition. 3 of the Earth's motions are completely independent of the motions of the sun and the galaxy. Okay? Now, that doesn't mean they don't have something to do with the sun, they're just independent of that. I don't know why they put them in this order. I would have put daily rotation first, but they put yearly revolution first. As we know, again, we'll have James being the sun. The Earth is always moving around the sun. It takes 365 days to make the full 360-degree revolution around the sun. Much more quickly than that, it's daily rotating around its axis once every 24 hours. So that means 365 days it takes to get around the sun over those rotations. This is the one not a huge deal, but it has nothing to do with the center of the galaxy. We wobble a little bit. Okay, we'll talk about this later, but this is, have you ever, when you're a kid, or if you didn't do it, see someone do it, play with a top, spin that top, and it just spins, and usually stands pretty close to upright as long as it's spinning rapidly. But then it starts a little bit of a wobble. Spinning really fast, but moving just a little bit. That's the third of our motions, and this is 24, rotates once every 24 hours, goes around the sun once every 365 days. This wobble takes tens of thousands of years to do. It's incredibly slow compared to the other two. So those are three of our motions that are completely independent of the motions of the sun or the galaxy. But we have 7 major conspicuous motions. Now, counting those 3 we just did, in fact, here they start with the rotation. Daily rotation of the sun, and by the way, at the equator, you're moving, you don't realize it, but you are, at better than 1,670 kilometers per hour, which would be in miles per hour. About close to 1,000 miles per hour. Don't realize it, but you're moving at about 1,000 miles per hour. Now, are we moving that fast? No, because we're 33 degrees north of that. So we're not moving quite that fast. Because if you think about it, spinning here, you are moving fastest where you go the longest in one spin. We're up here, so we're not moving as far in one spin as you are at the equator. Up here, you're not moving much at all, or down here. You're just sort of twisting, but you're not moving very far. So this is at the equator, okay? So if we're close to 1,000 miles per hour at the equator, I'd say we'd be maybe 700, 800 miles per hour where we are. Okay, so that's your rotation around our axis. The monthly rotation about the Earth, Moon, center of mass. What? Okay. Have you ever watched the figure skaters, the pairs during the Olympics, or the ice dancers and those kind of things? When they start spinning with each other, usually the guy being more massive will kind of fixed in place, and the guy moving around him, but they're both moving like this. Well, that's us in the moon. Remember, our moon, relative to our size, is the largest satellite to planet ratio of any in the solar system. We have an enormous moon for our size planet. Mercury, remember, has no moons. Venus has no moons. We have the one. Mars, I think, has 2, but they're little specks. I mean, Mars is much smaller than us, and their moons are trivial size, nowhere close to ours. Jupiter has 4 big moons, close to sort of the size of the Earth, but they are so tiny compared to Jupiter. Our moon is really big compared to us. I mean, we're bigger than that, but yeah. And then you go on to the others that nobody is close to having. Well, so when the moon is moving around us, we are kind of doing this. We're not perfectly still. We move a little bit. It moves a lot, but we move a little. Okay? In fact, the axis of rotation is somewhere about like this. If you imagine putting a spike through the Earth, coming out here, going in here, and out here, we move around that like this, and the moon moves around us way out there. But we are moving relative to the moon. When the moon's over here, we're here. When we're moon's here, we move here. We don't move much, but a little bit. So that's the monthly rotation about the Earth-Moon center of mass. Not huge, but a little bit. Yearly rotation about the sun. Okay, we're flying doing that. 106 kilometers per hour. That would be about 60,000, maybe 70,000 miles per hour. That's how fast we're moving around the sun. We don't notice it because we're on the Earth. We're fixed there. Now, the orbit of the solar system, that's the sun and all the planets and all the asteroids and meteors and comets and everything else about the center of the Milky Way, 370 kilometers per hour, which would be about 200,000 miles an hour. Okay, that is really moving. Now, the orbital motion within the sun's local star group, okay, so we're in a little group of stars with our sun, and in that thing we're going in that about 1 million kilometers per hour, which would be about 600,000 miles an hour. Now, the motion of the Milky Way galaxy relative to remote galaxies, we're moving the whole galaxy, which leads us to about 580,000 kilometers per hour, which would be about 350,000 miles per hour there. Okay. Those are 6 sort of conspicuous motions. This is not very big, but a little bit. How about minor ones? Okay. Changes in the shape and size of the Earth's orbit. Okay? Now, we'll talk about this a little bit later, but believe it or not, we don't quite have a circular orbit. It's slightly elliptical. All the planets have slightly elliptical orbits. The comets have extraordinarily elliptical orbits. Pluto has a pretty wide elliptical orbit, okay? But we're not quite perfect there. And are we approaching our closest approach to the sun or our furthest approach from the sun? To the sun. Okay. We're tilted, approaching being tilted to the sun in just, 6 days, less than a week. We'll be tilted to the sun as close as we're going to get. But guess what? In July, we'll be the farthest from the sun. Back in January, we'll be closer to the sun. The Earth itself will. But we'll be tilted away. We'll still be in winter. We don't notice that little bit of distance. But that's the difference they're talking about here. Changes in the shape and size of the Earth's orbit. Sometimes we're a little closer, sometimes further away. Changes in the tilt of the Earth's axis, that's that precession I was talking about, the top-like thing that takes hundreds of thousands of years to complete a trip. And, now this is the sort of a weird one, we're not traveling quite as fast as we used to. Kind of like me. No. We used to spin a little bit faster than we're spinning now. We'll probably slow down a little bit more. So we're slowing ever so slightly. Hasn't changed our time since we started measuring time, but if we live a few hundred, tens of thousands of years, we'll probably notice a little bit of change in the time. Okay? So those are minor motions. So this is actually 9 motions. They say 7, but these are 3 different ones here, so 7, 8, 9. Okay. But these are all pretty small, especially compared to how fast some of these others are going. Now, so if you just looked at us in space, we would be moving in what they call a helix, okay? I don't know where this picture is. In fact, I think they've taken it out of the new edition. I don't see it in here. But basically what this is saying is we're traveling around the sun at a pretty rapid rate of speed, but the sun's moving around in its local star group, and we're going with the sun. So as we're going, we're doing this, so that gives us this helical type path. I don't really care for this picture too much, but it's a fair rendition of what's going on. But then the sun's got so many motions relative to the star group, relative to the Milky Way, and then the Milky Way is moving too, so it'd be really hard to get all those changes in one picture. But the major ones would be, and this doesn't even show we're spinning too, so we're spinning and then going around the sun as the sun's going flying through space, carrying all of us with it. Okay.
Getting busy talking about
What's that?
it. So I'm getting busy talking about it.
Yeah, exactly, exactly.
It's a lot of movement.
Okay. Now, viewed from the Earth, it looks like the sun is moving along its ecliptic plane. It really isn't, okay? We are here, and when we move to there, it looks like the sun is moved from here to there, you know, but it really hasn't. It's pretty much where it was, and what it's doing, though, it seems to move around. But this is really the plane of our ecliptic, okay? The plane of our orbit around the sun, and we are looking at the sun relative to that, and we say the sun moves along its ecliptic. That was that dotted line on the starfinder we had, okay? The planets move in a narrow band around the ecliptic plane. The solar system is relatively flat, at least the part that are the planets, and pretty much the asteroids too, okay? If the Earth is here, Mars might be a little above or below, Venus, you know, Jupiter a little above or below, you know. They're basically in that same plane, that same disk. Pluto, on the other hand, does some weird things about 17 degrees out, you know, so it's way off that, you know, it's relatively far off that disk. And pretty elliptical, too. We are slightly elliptical, it's very elliptical. But then remember, you have the Kuiper belt, which is pretty much according to this, but then you have the Oort cloud, which is just all around it. And so it's not just the planets. There's a lot more to the solar system, as we learned in the last chapter. Okay? But when they say the solar system is relatively flat, they talk about the plane that contains the sun, the planets, moons, and the asteroids. And, you know, a little bit of the Kuiper belt, too, is sort of in that. The sun moves along the ecliptic across the background stars. No, it doesn't. We move around the sun. It just has the appearance of moving. But if you think about it, if some star is way back there somewhere, and another star is over here, when we're here, the sun's going to block that because that's going to be visible. The sun will be visible at day. But this star over here, we'll see, say, in the evening. Okay? But when we move over here, we won't see it anymore because the sun's blocking it. We'll see this one, say, in the morning. Okay? So it does seem like the sun is moving among the stars. We're really moving around the sun, making it look that way. Okay. So let's look at each of these motions separately. Now, in the new book, they're not following quite the same order they are in the slides, because the new book starts with the orbit. Okay? Well, actually, that is the same. Yeah, I looked at it wrong. The orbit revolution, that's the same. They're just using a different word. Orbiting around the sun, that's our revolution around the sun. That's the Earth's movement around the sun. The orbit defines the plane of the sun's ecliptic. We're the ones moving, it's not, so our orbit defines how the sun appears to move, and that defines the sun's ecliptic. The ecliptic is the apparent path of the sun. Not really, we're moving around it. So it's the apparent path of the sun through the heavens as seen from Earth. And what we're getting at there, okay, let's go back to James being the sun. And there's stars all back there, and here, and here, and here, and here, all around us. There's stars out there. They're not moving. They're fixed. I'm looking at James. It must be daytime. I can't see any of those stars back there because they're in the light of the day. But right around sunset, I might see these, and around sunrise, I might see those. midnight, I'll see the ones over here. Oh, he's way out of the picture there. I'll turn away from him, all right? Okay. So these I see pretty clearly. Next December, I'll be back here with Brian, and can't see those at all, can we? Because he's in the way again. He keeps getting in the way. Okay, but these will be, he's saying in the evening, that in the morning, ones back here when we turn and look that way that we couldn't see before, we'll see really, really clearly. So it seems like the sun is blocking them sometimes and others not. What it is, we've moved around and put the sun in between us. Okay? It's the apparent path of the sun through the heavens as seen from Earth. That was that dotted line on that star chart we had. This is ecliptic, when the sun eclipses some of the stars back there. This is the elliptical orbit, not circular orbit. And again, we're approaching our far away point, that'll be early July, from the sun, where we'll be closest next winter, around January. Okay, oh, here we go. We are about 2.5 million kilometers, it seems like a lot, doesn't it? Out of 193 million is not much, okay? But 2.5 million kilometers closer in January than we are in July. 2.5 million kilometers more distant in July. The Earth receives about 6% more solar energy. The Earth itself receives about 6% more solar energy in January. We don't, because we're facing away from the sun, but the Earth itself does. And it makes me wonder, how weird my thinking is, if we're facing the sun when we're farthest from the sun, okay, think about these poor people down here in the southern hemisphere. They are both tilted away from the sun and farthest away from the sun. It would seem like their winters would be more extreme than ours. And then in the summertime, in the wintertime, when we're tilted away from the sun, but are actually closer to the sun, these guys, it says summer and they're closer to the sun. So again, it would seem like, I don't know if it's true, I don't know if it's measurable, but that would be a good research thing to look into if anyone's interested, to see if their extremes of temperature are a bit wider than ours are because of that distance. Well, that seems like a lot, but again, out of 193 million, it's not very much. Oh wait, I'm sorry, not even that. This is 193 million miles from the sun. This is 2.5 million kilometers, so that would be about less than 1 million miles. Out of 193 million, that's not a lot of difference. Okay. But of that more solar energy received in January, those folks in the southern hemisphere are getting most of that while they're tilted toward the sun at the same time. So, seems like it could make a difference to me. All right, here's an exaggerated picture of that. Really exaggerated. June, we're not that much further than we are in December, okay? It's close. It's actually January and July, but July here, January there is one of the closest. They've exaggerated this big time. But we're tilted toward the sun then, and next week, around June 21st, the sun will be directly overhead where? At noon. Directly overhead at noon, where? Yeah, 23.5 degrees north of the equator, which is called the Tropic of Cancer. Okay? Yes?
How does that affect the hemispheres having seasons opposite each other?
Right here, so I got the question.
How does that affect the hemispheres having seasons opposite each other? Like in the southern hemispheres, next week will be winter time.
Yeah.
And then here will be summer.
Right.
How does that affect that?
How does it affect it?
Yeah, just how it's
They're invading Susan Christmas. Yeah. I wouldn't be surprised if they don't have their school breaks in December rather than having them in summer. Yeah, our summer. They probably have them in their summer. Yeah, it's just everything it seems backwards. Okay, but then too, if you live near the equator, nothing ever changes. You know, and it doesn't make a lot of difference. So if you live further north, it's a major difference as far as so little sunlight in the wintertime and so much sunlight in the summer. I would find going to sleep and sleeping well in the summer very difficult to do because I like it dark when I sleep. And even when we were in Canada, my wife's family used to take trips about one every 3 or 4 summers somewhere. We went up to Canada, in Alberta, Canada, which is here. We got just barely over into British Columbia, one of the trips. We were so far north here that it was sunsetting and it was in the summertime, I think around June-ish. The sun was setting like at 9:30 at night. You know, it made it hard to sleep. And then, of course, about 3:30 or 4 in the morning, there's the sun coming up again. You know, so you wanted to have really dense curtains, you know, to get a good night's sleep. The weather was great, but yeah, it does affect what we think of. You know, we think of wintertime being December. They just think of it as June, you know, and July. The coldest month of the year for them is July and August, not January or February. So it just is but they're used to it. They've lived there most of their lives. People who move, I'm sure that's a bigger shock to them. You know, if you change hemispheres. Yeah, it's a difference. But the seasons are just backwards. Okay, it's all it is. Okay. So here, these folks, like I say, when they're tilted toward the sun, they're also closer to the sun. Not by as much as this picture shows, but they are closer. And when we're tilted toward the sun, we're actually further away, which, if anything, should moderate our temperatures a little bit. Not get us quite as hot as we would have gotten in the summer, and not quite as cold in the winter, because we're a little bit closer to the sun. Okay? These dates here, this is when the ecliptic crosses the celestial equator, or actually our equator. That's in fall equinox and vernal or spring equinox. This is our summer solstice when the sun's highest in the sky, winter solstice when it's, for us, when the sun's lowest in the sky, which is also mean we have the least amount of sunlight in a day. So this shows again summer solstice here for us. This would be summer solstice for the southern hemisphere, okay? But this is winter solstice for us, autumnal equinox and spring equinox. This is also sometimes called vernal equinox. I count equinox meaning equal night and day, equal night. Not in German it's N-A-C-H-T or something like that. This is almost pronounced the same way. Solstice means sol is sun, cease means still. The sun stands still. In other words, it climbs and climbs and climbs every day, gets a little higher in the sky until around the 21st of July, June, and it doesn't get any higher, and then it starts going lower in the sky. And in December, it doesn't get quite as high up until December 21st or so. Then it sort of hangs in there for a little while, and then starts going a little bit higher. And that, I think I told you before, was part of the mysticism around the solstices. In the old days, the people always feared that the sun would keep going lower and lower until it disappeared, and then we'd never have sun again, and we'd freeze to death. But it never happened. So they always had a party around the winter solstice when it started going a little higher again. Yes, it's coming back again this year. Okay. So that was the revolution or orbit of the Earth around the sun. Now let's look at the rotation of the Earth and the Earth's axis. The Earth's rotational axis is inclined at our favorite 23.5 degrees, as shown, I guess, here. Yeah. Same as we had before. That tilt from here is about 23.5 degrees. Again, it looks like they exaggerated maybe a little bit there, but there it is. 23.5 degrees between the winter solstice and the celestial equator, or between summer solstice and celestial equator. Okay, 23.5 degrees. On the equinoxes, the declination of the sun is 0. We're right on the it's right on the celestial equator. Those 2 days only. Okay. The seasons are determined by the orientation of the rotation axis. The winter solstice is when the sun is lowest in the sky for us. Summer solstice when it's highest in the sky at noon. Spring equinox is when the ecliptic crosses the equator, celestial equator. In the springtime, same thing. The autumnal equinox, they cross again. The celestial equator is the line on the celestial sphere above the Earth's equator. So if this is our Earth's equator here, the line on the celestial sphere would be the celestial equator, and that's what we've been referring to repeatedly in the first 2 labs. The next lab will not be quite like the first 2. The first 2 were, I thought, fairly similar. The second one introduced the analemma that you didn't have in the first one, but other than that, you were doing a lot of the same things, drawing the things and stuff. But the next lab will be a little different. In many ways, maybe a little more fun. In other ways, more on you, okay? Because there will be 3 questions that you have to answer based on observations you make in about a 2-week period. So you're going to be working on the next lab, not continuously, but just by every other day. You'll need to do something for that lab if it's clear at night, and do. We'll get to that later. Okay? Now, dumb question here. Does the Earth rotate? Well, I don't feel like we're spinning, do you? I'm not getting particularly dizzy. Okay? How? Well, what are some evidence that we have that truly it does rotate? Okay? And I think that good old Galileo was the first one to see this. When he perfected or improved upon the telescope that someone in Northern Europe had developed, he read about, heard about, and he sort of copied and made big improvements, he saw Jupiter for the first time as a planet rather than as a star. You know, it just looked like a fairly bright object in the sky until he looked through his telescope and said, hey, this is a big ball, and that big ball is spinning. Well, I don't know if people had before him noticed that about the sun or not. Probably had, I don't know. Maybe that's where Copernicus came off, I don't know. But it's hard to look at the sun. But as people developed techniques they saw, hey, the sun seems to be spinning too. This sunspot that we saw here the other day is now over here, and now it's here. Disappeared, it came back later. Okay? So the sun is also spinning. So if those 2 objects obviously are spinning, why wouldn't we be spinning? So there's one piece of evidence. Here's another. Have any of you been to McWane Center? Okay. Isn't that a fascinating place? I mean, they got so much going on there, and it's pretty. When you were there, did they have a big pendulum over in one corner that goes back and forth? Did they have that? It's about, at one time they had a ride you could ride across the top. It was a pretty scary looking thing, but you know, they had it balanced and everything. You could ride there, but it's a huge pendulum. You can there are other places that have those. I don't know if, I haven't been to McWane in a couple years now, so they may not have it, but they used to have it there. If you followed that pendulum, if it was just free to spin, to move, today it could be moving from Ricky to me. But then, this evening, say around 9 o'clock or so, it may be moving that way. And then it'll move that way, and then it'll move this way, and then tomorrow about this time, it's moving this way again. Now, why is it ever so slightly changing? Because the Earth's spinning. So Foucault pendulum, I think that's how you pronounce it, pendulum that oscillates in a fixed direction. Only the trouble is that direction is absolutely fixed. It changes ever so slightly over the course of a day. The orientation changes as the Earth rotates. Now they have a diagram here that, they have this as figure 1610 in your book as well. And by the way, 16.9 is, I think, Foucault. I believe that's the one of actually him talking about and illustrating his pendulum. Okay. But hey, there is a picture in the book. This is new in this edition, figure 16.8. It shows the sunspots, and at different days when you took pictures, they were in different locations, meaning the sun was actually spinning. Okay? Let me see. Here's example 16.1. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on the summer solstice? Interesting question. Okay? What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on summer solstice? Well, all we know, noon, maximum day of the year, 38.5 degrees is where the sun is above the southern horizon. Now we know the sun is what relative to the celestial equator? 23.5 degrees above. So that means the celestial equator would be down there. Subtract 23.5 from 38.5 and you get 15.5. No, 15 on the nose. 15 degrees would be how far the celestial equator is above the southern horizon. Then what would the angle be from celestial equator to the zenith? No, celestial equator, that's the horizon to the zenith. Subtract 15 from 90 and you get 75. That's your answer, 75 degrees north. Okay? What is the latitude of an observer who measures the sun's altitude of 40 degrees above the northern horizon at noon on summer solstice? So this time the sun is 40 degrees up. Okay? You know that celestial equator is 23 and a half degrees below the sun. So you subtract 23.5 from your that 40 degrees and you get 26.5. Okay? Above, okay. They don't have the answer right, I don't think. They forgot a subtraction there, okay? You subtract that from 90 and you get your real answer. So we won't go into that because they missed it, it looks like, anyway. So there's the second. And here is a illustration they gave. If I were to set up a deal and have a stool that swung freely, deal like this, and had an object going back and forth, okay, but then spun the thing, then it would be doing like this, okay? That's exactly what a Foucault pendulum does. One time around, it goes through every thing. Each swing is so minutely different from the previous one, you don't ever notice it until you look at it several hours later and say, hey, it used to be here, it's now over there, okay? All right. And then one more. The Coriolis effect. By the way, there's a potential paper topic. Who in the world was Foucault? Who in the world was Coriolis? That would be another paper potential. Or what about, how did he discover this Coriolis effect? Or what is it? What difference does it make? It's the deflection of the paths as the Earth rotates between moving objects. Okay. Have you ever, I'm guessing you guys more than you gal, when you were young, ever dream of being a bomber on a plane? And you drop the bombs and what you, either way, it always seemed like it would be a fun thing, you know, to see them go. But guess what? If you're dropping from a very high altitude, it doesn't fall straight down. Because while it's falling, the Earth is spinning, and that puts a little deflection in. So all of, when I was in the Navy, my last year on my first ship, I was the gunnery officer. And as such, the gunfire control people worked under me as the gunner's mates, and they had to always do the calculations in their computers did them for them, but they had to calculate and take into account that things they are moving, you know, when you fire things from high distance. Now, surface of the ship to another place is not going to have a huge effect, but it will have some. But here's another result of the Coriolis effect. Have you ever noticed when you pull the plug in the sink or the tub or flush the toilet, does the water just go straight down? What happens? Always spins. And if you've ever noticed, always spins in the same direction. Why? The Coriolis effect. Because the Earth is spinning, and we don't notice it, but the water does, and it creates a little bit of a torque, and it does that motion. Okay? Now, this is an illustration of just how weird physicists are. I think it was my junior year, what many people consider was one of the toughest sequences of courses that Georgia Tech offered. It was Physics 301, 302, and 303. I think it was either 301 or 302. I think it's 301 I had Dr. Young, I believe his name was. Yesterday I was telling the same story, I couldn't remember his name. Dr. Young for the 301. And we were talking about Coriolis effect, or he was. How weird physicists are. What? Have any of you ever heard of a city called Rio de Janeiro? It's in Brazil. There it is, Rio de Janeiro. Right, almost on the tropical capital. Okay? So it's a tropical city. The largest city in Brazil, Brazil is the largest country in South America, one of the largest in the world. The major city is Sao Paulo. I can't find it now. Not that far from Rio, but, oh, there it is, Sao Paulo. Okay? Means Sao Paulo. Okay? That's the biggest industrial, money-making, busy city. Okay? Rio de Janeiro is another really big city. But it's party time. I mean, they have festival, they know how to celebrate Rio. Okay? Now, the capital of Brazil is Brasilia, which is way inland and it's not nearly as big. In fact, that's a manufacturing city. They built it just to be its capital. Okay? Well, this professor I had was a honcho in crystallography. And that's a branch of physics. And he was like editor-in-chief of the crystallography magazine, or journal, you know, and he was up there. Everybody in crystallography knew him and knew of him, and he was quite a well-respected scientist. And here he was teaching this group of juniors in college, you know, this thing, and he was a real nice-seeming guy. And they were planning to have, or no, they had the crystallography meeting, the annual International Crystallography meeting in Rio de Janeiro, the party city of the Southern Hemisphere. I mean, it's just a fantastic place to go and have a convention. Okay? And he said he was so excited when he got there, and the plane landed, and they got him to his hotel. He was so excited to be there. You know what the first thing he did? He ran into the bathroom and flushed the toilet because he wanted to see the water go. Poor old society. There he was, party city of the Southern Hemisphere, and wanting to flush the toilet. Watch water go down. Never mind. Okay. That's an effect there. And by the way, that's why all your hurricanes, tropical storms, thunderstorms, tornadoes in the northern hemisphere spin the same way. In the southern hemisphere, they spin the other way because of the Coriolis effect. So, a lot there if you're interested. Okay. Another indication the Earth is spinning. If the Earth wasn't spinning, we wouldn't have that effect. Okay? All right. I don't know if there's a picture that's supposed to go there. I don't see one, so let's move on. Now that next one. The one that is so slow compared to how fast the others are. This is precession. That's a very slow wobble of the Earth's rotation axis. Very, very slow. That's a reaction of the Earth to the gravitational pull on the equatorial bulge by the moon and the sun. Okay, whatever you mean. Remember, there is a bulge on our equator, the Earth's too, okay, and because of that reaction that the sun and the moon pulling on that a little bit stronger than they do on the poles, that makes us wobble just ever so slightly. 26,000 years for one precession of the sun. And we'll never notice it. Ever notice it. We live 70, 80 of those years. We'll never notice it. In fact, recorded history, we haven't seen but very minor results of that precession. Now, it changes the direction of the rotational axis on the celestial sphere. The stars are in the same place, but we just point to a different one. Polaris was not always the North Star, nor will it always be our North Star. Right now, due north is almost directly pointing to Polaris. Not quite, but pretty close, okay? When we're at the planetarium, you'll probably point out Vega. I think we saw it on the star chart, okay? Vega was one time, if I'm not mistaken, our Polaris, our North Star. Much brighter, much more obvious, but we've moved away from that and are now closer to Polaris. That means sometime in the future, not during my lifetime or probably even yours, you'll find out that there won't really be an exact North Star. North Star is going to be fairly close. It's probably not right on the money now, but it'll be even further off later. And then sometime or another, there'll be another star that's a little closer. And then over maybe another 12,000 years, it'll finally hit Vega again. Okay. The position of the equinoxes on the zodiac changes. Now, this is one thing they have noticed a little bit. Those zodiacal signs, I don't know how you pronounce that, you know, Taurus and Leo and Sagittarius and all those. Those are, second, Scorpio, yeah, all those are on the ecliptic, okay? On the ecliptic, and at different times of year, the sun is in Leo or in Taurus or in Scorpio or, you know, because it's blocking them, because it's lined up with them. There's one, I don't remember which, actually the constellation either a little north or a little south is now closer to the ecliptic than the one that we named. But that's always been, so they kept it. So actually, those constellations are not quite as close to the ecliptic now as they once were. Neither are the position of the equinoxes. Okay? And this is a greatly exaggerated evidence of this. If that were the Earth rather than a top, and we were not only spinning quickly, but also wobbling ever so slowly, maybe the North Star is right there now, and over there it's going to be Vega. And there could be other stars in between. But as said, once every 26,000 years, we'll never notice it. Okay? This is the one that actually shows the Earth. Now, again, it's pretty expanded. It's not this big of a change, but today, that's pretty close to our North Pole. Okay? Not exact, but pretty close. And sometime over time, it will actually get further away from the North Pole as we spin and spin and spin. We'll sometime have no star directly there. That may be our closest one. We may run into some other stars that are closer to that one and easier to see. So we may have other North Stars at other time. But then at some point we'll be over here about 14,000. Okay, we've been around. This is now just 2100, right? 2017. We're in the 21st 100th century, or something like that. So, okay, bending at time was not zero. It was maybe 3,000 years before that we started really recording history well. So what? We've been around recording things for about 5,000 years. This is going to be 12,000 years from now before we ever have that. So I don't even know if we'll still be here. We may have destroyed ourselves. We may have destroyed the planet. We may have poisoned ourselves with our atmosphere. Who knows, whether we would ever be here to realize and see Vega as our North Star or any of our descendants. Okay. All right. That's precession. Happening so slowly, there's very, very little direct evidence of it right now. Okay, 16.3. Okay, place and time. I think we've hit this in other chapters as well, so let's just hit it again. The Earth's periodic motions provide a basis for determining place and time. Okay, now I'm real tempted to jump into that and start explaining it. I think the next few slides will do a better job. So we'll just leave it like that now. The rotation provides an axis of rotation useful for determining location. So that's where the place comes in. Because we do have an axis, okay? There it is, the north-south pole, that's our axis. That line that goes through there, the Earth spins around that. Now notice that's not changing. It's wobbling, but it's not changing. It's not that we're spinning around here and then later over here. We're not doing that. That's our axis. And because that's our axis, that gives us a really easy way to determine the equal point from these two ends of the axis. Equal points would be equator. Equal distance from north and south poles all around the globe. So that gives us a reference. Say again? Okay. So that gives us one reference. And then we can see how far we are north or south of that in degrees, not distance, but in degrees. That gives us what we call our latitude. Later, a couple labs from now, when we can't really do anything with that chapter, we'll come back and do latitude and longitude. Okay? So that gives us a starting point. The fact that we do rotate around our axis, we take the points on the axis and name those the poles, 90 degrees north and 90 degrees south, and then equal distance from that is the equator, 0 north, 0 south, and then they go up and down from there. Now, the rotation and revolution together determine cycles which we can use for time standards. Okay? So let's go over those real quickly. The rotation of the Earth basically gives us what's time standard. One time around is about equal to 1 day. Okay? One revolution around the sun gives us what? 1 year. Okay? Now, we have this other body out there, closest body to us. So it looks pretty big, but it's not nearly as big as the sun, but it looks next biggest. Moon. And guess what? One change of the moon gives us. Moon is M-O-O-N. Drop one of the O's, and what do you get? M-O-N-T-H. Months! That's why we have 12 months, because we have approximately 12 cycles of the moon in a year. It's not exact, it's close, but it's not exact. Months, moon, rotation of the Earth day, and the revolution of the Earth around the sun year. So yeah, our rotation, our revolution, these gives us useful time standards. Now, I don't know of any reason that we have weeks of 7 days except for the biblical record. I don't know if that's the reason. I know most of the planet doesn't do it, but it seems to have permeated everything. So we have 7 days in a week, but there's no astronomical thing that I can think of that would give us that. Except you have this is true. The moon has 4 quarters. You go from a new moon to a half moon to a full moon to a half moon to a new moon once a month. So you divide a month into 4 pieces and you have about 7 days. So maybe there is another reason. And maybe, okay. So the phases of the moon might give us our weeks. All right, now, we've already started about identifying a place. If we lived on a flat Earth, and I know there are societies that think we still do, flat surface, they'd be real easy to figure out where we were. Intersection of 2 straight lines is always a point. Guess what? On a sphere, or a spheroid, a curved surface, you don't quite have those same easy intersections. Okay? You do have some intersections, but they're not necessarily perpendicular. Okay? So if you had a point on a page and you want to identify how to find that point, you would say from the center of the book, go down so many centimeters or inches or whatever, stop there, and then go to the right so many more centimeters or inches or whatever, and that then identifies exactly where you're on the page. You're so many times from the top and so many over from the center. That would be what you would need. This is from the left side of the page, this is from the top of the page. That would give it to you. Or you could say this is from the bottom of the page, this is from the right side of the page. Doesn't matter, you can always identify exactly where you are, 2 coordinates, horizontal, vertical. Done. Doesn't work that way on a sphere. Okay? In a sphere, what you have to do is, like I said, identify that equator. That's the equidistance from the North Pole to the South Pole. Equal distance, equal equator. And then from that, imagine you were in the center of the Earth. It couldn't be, you'd be burnt to a crisp, melted, okay? Oxidized, I mean, you'd be gone. But if you were there, imagine to here that would be 0 degrees, up there would be 20 degrees, 40, 60, 80, 90 degrees. So you do that from the equator north or from the equator south. So these are called several names. One of them are your parallels, because each one of them is parallel to the other. They never cross. Another name for them would be latitude lines. Latitude meaning how far north or south you are of the equator. tried to think if there is another name. Those are the two major ones that I can remember ever reading about. The parallels or the latitude lines. To me, latitude lines are far better than parallels. The book shows them as parallels. Okay. So this is what I said. Imagine you were at the center of the Earth. You had a protractor sitting at the center of the Earth, and it wouldn't melt or burn or something. And you measured how far up you were, 20 degrees north, 40 degrees north, 60 degrees north, or 90 degrees north. That would be where you are relative to the equator. Okay? That doesn't tell you where you are on the globe. It only gives you a fixed line. Now, we are at 33 degrees north, so that would be somewhere right around here. I'm sorry, somewhere right around here. 20 and 40, so we'd be more than halfway, somewhere right about there. But somewhere on the surface of the globe. There are lots of places out 33 degrees, 23 minutes, 45 seconds. Let me just pick out a few. Atlanta's not far from that, maybe just slightly further north. Columbia, South Carolina might be just slightly further north. Little Rock definitely is a little further north. Dallas is not far off. It may be a little further south. But guess what? You can go over to, maybe hard for you to believe, but Los Angeles, California is not far off from that. Okay? Almost the same latitude. Okay? Let's go to another continent. Pick some more that might be there. Okay? Just having a guess here. In Algeria, there's a little place called Jifa, or something like that. Almost exactly our latitude. Okay? Fez, Morocco. Rabat, Morocco. Very close to the same latitude. In Tunisia, there's places there, western cities there. So there's tons of places. The island of Crete is not far off from 33 degrees north, sitting out there in the Mediterranean Sea. My nephew was stationed on Crete for a year. Okay? So you can just keep on going. Where a lot of the really terrible fighting is going in Syria. In Syria is very close to our latitude. Iraq. That is very close to 33 degrees, 23 minutes and 45 seconds off the equator. So there's a lot of places that would have that part of the address. So just knowing our latitude is definitely not going to get us home. Okay? It gets you the right place, north or south of the equator, but that's all. Okay? We need something else. Okay? What is that something else? We need something east and west. Latitude is north and south of the equator, so we need something east or west. Well, the equator is a real nice thing to do because it's equal distance from the North and South Pole. What's equal distance from anything east or west? There's not. There's no place that you can say, this is where east begins or west begins or east ends or west ends. They name towns that, but that's all. Okay? So people had to sort of arbitrarily choose a starting point. Now, if I were to say, name the most major maritime country in history, in other words, what country is best known for its navy over long periods of time? Second? Britain, absolutely. Queen of the ocean, okay? She's an island country, and she had tremendous fleets. Her empire, they used to say, the sun never set on the Union Jack. always someplace where it was daytime. That was the British colony, protectorate, Commonwealth nation. Okay? The sun never settled. Okay? So, since Britain was queen of the ocean, we used navigation mostly for ocean purposes. They chose, or someone chose, where the British Royal Naval Observatory was, and that happens to be a town. I don't know if it shows on here. I think it does, but I can't see well. It's called Greenwich, England. Greenwich, England. Just a little bit, if I'm not mistaken, a little bit east of London. Not a huge amount, but just a little bit east of London. You might almost say a London suburb, but it's a little further away from that. Okay? The Royal Naval Observatory in Britain was there in Greenwich, England. They said, that's good. Let that be the zero east and west. So they call that line the prime meridian, meaning number one starting point for all your meridians. Now its measure is not one, it's zero. Zero east, zero west. That's the one that goes to Greenwich, England. Okay? Now, so from there, we can do, then we'll go, if we're going east from there, you can go 180 degrees. Now remember, the equator, you went north 90 and south 90. That added to 180 degrees, but you only went north or south 90. But now, since you're doing one of these, and by the way, and this is just a little feature, the equator is the only horizontal circle on the globe that is what we call a great circle. In other words, it's exactly one diameter or circumference of the Earth. Okay? All the other parallels get smaller as you go up and smaller as you go down. That's the only great circle. These meridian, they are all great circles because they all pass through the north and south equator at the same time. Pass through them. So they're all great circles. Of your latitude, only the equator is a great circle. Okay? So therefore, you're measuring east from there to 180 degrees. We stop there. Or we measure west to 180 degrees and stop there. So this is the prime meridian on this side, where it's 0 degrees east or west. There is a name for the one on the other side, the 180. Does anyone know that name? International Dateline. Why? Okay, just imagine this. Let's say it's noon on the prime meridian, 0 degrees, Greenwich, England. Dead noon. If you started going this way, counting backwards, that would be 11 o'clock, 10 o'clock, until you get to midnight on this side, right? Well, if you counted around this way, that's 11 a.m., 10 a.m., 9 a.m., 8 a.m., okay. Counted this way, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, until you got to midnight around here, right? But this would be midnight the same day you were noon here, and this would be midnight right before the next day you got there. So that, when you cross that line, you can change a day, okay? You either add a day or you lose a day. Just like when we flew from here to Atlanta, we lost an hour. But then when we flew Atlanta to New Orleans, we gained an hour back, okay? Depending on which way you look at it. And then when we flew from New Orleans to Atlanta, we lost an hour. And then when we flew back to Birmingham, we gained it back, so we wound up on the same time that we started. Well, when you go across that one, you cross a day, and it may be Thursday on one side and Wednesday on the other, or Friday or whatever, like that. So that's called the International Dateline.
Next question.
Yeah.
I have seen events go on, like something supposed to happen in England or
Right.
in Australia, and they'll say UTC time or something like that. What is it called?
GMT?
It'll be UCT. universal time?
They may have another name for it. It used to be called GMT, Greenwich Mean Time.
Okay.
Okay? Yeah. Now, in the Navy and in most of the militaries, you call it Zulu. Okay? I don't know if you ever saw the television show JAG. Judge Advocate, it was a naval JAG officer, and he had a Marine JAG officer as an admiral. No, he was an admiral, wasn't he? So he wasn't Marine. He was a SEAL or something. But anyway, he was his boss, and it was Rab, tall, fairly nice-looking guy. He had a Marine Marine that was his partner, sort of. And but they always gave GMG in Zulu, Greenwich Mean Time, because the Navy, when you're keeping certain logs, you always do Greenwich Mean Time, because if you're going around the world, you might have 2 1 o'clocks in one day. So which one are you talking about? So you keep everything by Greenwich Mean Time. It might say 0700 to be in the middle of the afternoon or late in the evening, but it's still 0700 GMT or Zulu. And they used to always on JAG get the Zulu time, okay, which is really bizarre. No one ever paid attention to it, but that's what it was. Yeah.
Okay, I just looked it up. It's UTC.
Okay, where is that?
I looked it up on
Oh, on your phone. And what is that called?
Coordinated Universal Time.
Universal time?
Yeah. And it's 7:41 now for us.
Yeah.
Universal.
Okay. That means that's what time it is in Greenwich, England.
Okay.
So, or that's what I assume. Now, let's see if that's right. They are 7 or 8 hours either ahead or behind us. Which way is it? They're ahead of us. So that means, I don't know, it's 7 o'clock, or 07, you said, or 1900?
7:41
PM, okay, yeah, 1900. Yeah, that makes sense. Okay. Yeah. That's what time it is in England at this time. Okay. So that's how we get our second dimension. So whereas on the board it was horizontal, vertical, now we do latitude, that's sort of north or south, longitude, east or west, around the globe. Okay. So any position you are on the Earth, you have a fixed latitude line and a fixed longitude line. So it's the intersection of the parallels, latitude, and the meridians, longitude, defined with respect to the rotational axis. So the parallels are called your latitudes, and your meridians define your longitude. Now we've been dealing with how far north or south we are from the equator over and over, but we haven't mentioned longitude. The 90 degrees west of Greenwich Mean goes right up through New Orleans and Jackson, Mississippi, and Memphis, Tennessee, pretty close to St. Louis, Missouri, pretty close to Madison, Wisconsin, running out of noticeable cities after that, okay? And south of us, there is not much there except ocean. It does go through Guatemala, the Yucatan Peninsula in Mexico, and just the very edge of El Salvador, and the rest of it. But the Galapagos Islands are right close to that 90 degrees west too. And then you get on down to South America. Nothing but ocean in between. So that's 90 degrees west. A quarter of the way around the globe from Greenwich Mean. Okay. Now we're a little bit east of that, so I can't remember now, but we're like 87 or something like that degrees east. Not quite to 90, but close to it. I mean degrees west. Okay. So if you know your latitude, longitude, just like on the board, you know exactly where you are. pinpointed. But you have to have north-south for latitude, east-west for longitude. If you don't have those, you don't know which side you're on. Okay, so this is showing the same things again. Seems like we've just seen this. Again, latitude lines or your parallels are degrees north for us or south of the equator. Okay, 0 to 90 north or 0 to 90 south. Okay, same picture we had before. I was so tempted that this morning, they were saying a chance of thunderstorms later in the day. I was thinking, yes.
In my first place.
Yes. I was in the registrar's office asking a question about something, and they said, "Is that rain?" And I said, "Yeah." And it was, and they were saying late in the day. So this morning, it was so hot this morning, I wanted to roll down the windows a crack, and I thought, no, they said it might rain later in the day. I don't want to risk it. So I left them up. I'm so glad. Okay. And then east and west, your longitude lines. Greenwich Mean Line, the prime meridian here at 0 degrees, and then you go east, that's going toward, through Europe, Asia, and all around like that, west, across the Atlantic, and to the U.S. and South America, and all around to the Pacific. Okay? So that's the second dimension of place. And there it just shows a different picture of it. Same one we saw before. Meridian lines are your longitude lines. They would be east and west. You've got to have that letter with it. Okay? Now, there are some very special parallels, and we've mentioned, I think, all of them, but let's do them again. Very special parallels that are related to the climate. Can anyone think what they are?
The circles in the tropics.
Okay, and what are they called?
Tropic of Cancer.
Cancer in the north,
Tropic of
Capricorn in the south. What's the circle in between?
Equator.
Equator, that's another important circle. Okay, going to go up a little bit further.
Arctic Circle.
Arctic circle on top,
Antarctic.
Antarctic circle on the bottom. What are those determined by?
I guess latitudes.
You're 23.5 degrees. Your Tropic of Cancer, 23.5 degrees north of the equator. Tropic of Capricorn, 23.5 degrees south of the equator. The sun is directly overhead, somewhere in between those two things, always. Never directly overhead here or here, but sometime of the year is directly overhead, always somewhere in the tropics. Okay? How about these up here? Arctic circle and Antarctic circle. What would those be defined by? 23.5 degrees from the North Pole from the South Pole. So you subtract 23.5 from 8960, okay, and you would have 6630. 6630. And that is your tropic of the Arctic Circle if it's north, and Arctic Circle south. What is determined by those? Those are anywhere above the Arctic Circle, one day of the year at least, you're going to be totally without sun. And one day of the year, your sun will never set. The further north you go, more days will be without sun in the winter and without darkness in the summer. Same thing down here. So all those are determined by the tilt of the earth. Okay? Those special parallels which are climate related. Okay? And why do we say climate related? Again, in between the tropics are the tropical, warm, usually moist, but not always. Sometimes monsoonal, but not always. But those are your warm areas. Okay? These are your very frigid areas above the Arctic Circle or below the Antarctic Circle, extraordinarily cold. In between those, the tropic and the Arctic and Antarctic circles, these are called the temperate regions. That's where we live. That's usually meant, yeah, we're not as hot as they are down there, but not as cold as they are up there, okay? We're more temperate, okay? You get more direct radiation, sun radiation in the tropics, very little on the thing. Even when you're tilted toward the sun and the sun never sets, look at the angle the sunlight comes in at. You have to pass through so much atmosphere before you get there, it doesn't get warm. Even though the sun's up all day long, it never warms up. Because when the sun's up all day long, it's just above the horizon at midnight, and then just barely gets a little bit further up in noon, and then it's barely above, it never gets high in the sky, ever, in the Arctic regions. Okay, we call those the Arctic regions. Whether it's Arctic or Antarctic, we call them Arctic regions. Okay. The main thing that determines temperature is the angle at which the sunlight gets to you. In the tropic, it's almost always directly. Least amount of atmosphere you go through, so that's why they're warmest. Up here, the most amount of atmosphere, so you lose so much energy going in. It's cold even in dead summer and just really frigid in dead winter, okay? The temperate regions, you get moderate between the two. You get a little closer to direct sunlight, never direct overhead sun in the summer, but closer to it. In the winter, you're further from it. So it gets fairly cold, especially the further north you are. So those parallels are your climate-related parallels. The equator, the two tropics, Capricorn and Cancer, and the two Arctic circles, which are Arctic and Antarctic. Okay. I'm guessing that's a pretty good place to pause, don't you think? We will pick up with measuring time next time. Okay? And I believe, no, I was going to say I believe we'll finish the chapter in the first hour and a half. I don't believe so. I was thinking the Earth part of it we would finish. We've still got the moon part to go. So I have a feeling next time we'll have most of the time on the chapter. Maybe right at the end we'll start the lab. We'll see. As I said before, the lab for this chapter is some in-class lab, and it's sort of fun. And then the rest of it is fun too. You'll be doing at home in about a 2-week period, over a 2-week period. You'll be observing the moon and registering those observations. Okay? So, we'll talk about that probably at the end of the class next time. Any questions? Okay. I know a couple of you have taken breaks. Do you want a little break before we start the test? Or you want to just keep going? Okay. Well, then let me pause this.